Hi everyone, my name is Chippy Joseph and I'm a student of MTech VLSI Design. I'm hereby presenting my seminar on SOC design. This is the information on the base paper which I'm going to present now. The title is High Throughput Energy Efficient Network on Chip Based Hardware Accelerators. It is a journal published by Elsevier which is published in the year 2013. So, as the title suggests, the paper presents a network on chip based hardware accelerator which has high throughput and which is highly energy efficient. For several applications, it demands high throughput, maybe in the range of terascale, and it requires even more higher performance. We know that the conventional multi core architectures are able to achieve a limited computational throughput. This is because of the inherent multi-hop nature of the network architecture. And we need to actually improve the bandwidth and energy efficiency. In order to achieve this, in this work, they have proposed to insert long range links which act as shortcuts in regular NOC architecture. The on-chip network is built using both wired links as well as wireless links. Wireless links are used as long-range shortcuts to reduce intercore latency. Now we will move on to a little more technical aspects of the architecture. This is the proposed use case model which is designed based on NOC architecture for hardware acceleration. And this is the multi-core SOC hardware accelerator which is proposed in this paper. And this is the CPU. The parent process or the main process is run by the CPU and it communicates through the interface. This is the interface here, and the PCI means peripheral component interconnect. It is a standard for connecting computers and their peripherals. Here there is a job queue and each rectangle here represents a function, and the area of this rectangle is proportional to the amount of computational resources that are requested by the CPU. The jobs queue is offloaded by the CPU to the master controller and again to the SOC hardware accelerator. This is the master controller, and the duty of the master controller is to allocate computational nodes to each function. These are the computational nodes, and each computational nodes are custom designed and it is lightweight, which is embedded in the NOC. Each computational nodes are connected to one another using either wired or wireless links. Uh, and if the computational nodes are assigned to a job, they stay busy till the execution of that particular job, and then the result is sent back to the CPU via similar interface. Here the same interface PCI is used. Here both wired as well as wireless links are present, which contributes to significant savings in latency and energy. Also, the long-range links reduces the overall network diameter, and it also enhances throughput by reducing the inter-core communication latency. Now we will see how the long-range links are designed in the NOC architecture. The cores consist of lightweight custom-designed processing elements or PEs. The on-chip network is folded torus, and it is a type of switchless interconnect topology. In the following slides, we will see more about the processing elements, the network architecture, dynamic node allocation, and on-chip routing. Processing elements are nothing but computational nodes. Here, the diagram represents the data path architecture of one processing element. Like this, many number of processing elements will be present in a multi-core system. And how many number of processing elements are there? That represents the size of the multi-core system, which is represented by a letter N. And we have already discussed that the processing elements are custom designed. That means we can include any number of operations in the processing elements, like all the scientific operations, the uh, anti-log functions, log functions, exponential function, etc. Here, only logarithmic function, anti-log function, as well as addition is involved. Here, as we can see, we need the sum of products of inputs A and B. For that, we have used log function as well as anti-log functions instead of using the multiplication process. Here, the logarithmic converters are present, and here anti-log converters are present. The inputs A1, B1, A2, B2, A3, B3, and A4, B4 are fed to the logarithmic converters, and the output of this is fed to the anti-log converter, and again it is given to an adder, and finally we are getting the product. Product A1, B1, A2, B2, A3, B3, and A4, B4, which is added together. Here, 64 bit is used to represent the number. Um and the number system used is fixed point hybrid number system. It has high efficiency and accuracy in representing floating point numbers. And Verilog HDL is used to design the processing elements, and the synthesis is done with 65 nanometer standard cell libraries. Now we will see about the network architecture. Here, a folded torus network architecture is used. The reason for choosing this type of network architecture is that the traffic patterns will be dynamically changing. This means that when a job is assigned to the nodes, only the nodes which executes the same job are communicated each other. When the next job is allocated, then some other nodes may be communicating each other. So this means that the traffic patterns are dynamically changing. We had already mentioned that the data path size is 64 bits, and so the flit size is also 64 bits. Flits are nothing but flow control units, and each flit consists of a header, body, and tail. Also, each internode link has minimum bandwidth of 64 gigabits per second. Here, the diagram represents the number of flits per cycle for an 8 by 8 folded torus network. The first one represents the mean, and second one represents the standard deviation. We ideally want the average internode distances between the nodes catering to the same job to be as low as possible. But we know that every time it is not practically possible. Different jobs may require different number of resources during any time. So we may have to wait to get the contiguous resources to allocate the job. This may increase the delay also. So there are two approaches here. One is to wait for all required nodes to be available contiguously, and second is to map the job on nodes that could potentially be non-contiguous along the network. Both has its own effects. Um, for the first one, that is, if we are waiting for the nodes to be available contiguously, then it will increase the execution time and it will lead to the non-optimal use of the cores. The effect of the second one, that is, if we are potentially mapping the non-contiguous nodes in the network, then effect is the increase in the average internode distances. So to avoid this effect, long-range point-to-point shortcuts are implemented to improve latency and network throughput. But there is also some other problems by implementing these shortcut links. That is, there may be disadvantages associated with the long wires and also the transmission delay if we are using the metal wires. So these drawbacks can be avoided if we use on-chip wireless shortcuts. Now we will see how the wireless links are placed in between the nodes. In order to establish wireless links, on-chip antennas are required. Here we use CNT antennas, which is nothing but carbon nanotube antennas. It can provide the frequency range up to terahertz. Dedicated and non-overlapping channels are also produced using frequency division multiplexing technique, and the different carrier frequencies are produced using the CNTs, which is of different lengths. That is, the length of the CNTs are proportional to the wavelength of the waves produced by it. Our requirement is to have 64 GB per second bandwidth for each wireless link. but each wireless link channel can provide only 10 GB per second. So what we can do is we can combine 7 channels for one link. So we will get 70 GB per second bandwidth, which is sufficiently higher than what we require. With the current technology, it is possible to create only 24 non-overlapping wireless channel with data rate 10 GB per second. So a total we will get 240 GB per second. What we require is 70 GB per second for each link. So if we divide 240 by 70, we will get 3, which is the maximum number of single hop wireless link that can be implemented using the current technology. This figure shows the comparison of average network communication latencies for different wireless link placements. As only 3 wireless links are available, we can place it anywhere in the architecture. And the experiment shows that when we are placing the wireless links along the diameter of the structure, we will get minimum delay. In this diagram, these red colored dotted lines represent the wireless links along the diameter, uh, and this diagram will be elaborated more in the next slide. So as mentioned earlier, we can have at most 3 wireless links, and we will be confused where to place these 3 wireless shortcut links. Ideally speaking, we should place these 3 links where the traffic is very much high. But the traffic patterns are arbitrarily changing, and it cannot be predicted. In the practical observation, we would find that we will get best results if we place these wireless shortcut links along the diameters of the network. In this diagram, we can see the overall network is divided into 4 quadrants, and the mean distance between the adjacent quadrants is the network diameter of the folded torus. So the 3 wireless links are placed between the adjacent quadrants um, along the diameter of the folded torus, such that almost equal angular separation is existing between each pair of diameters. Um, and this ensures that nodes in all sections of the network have similar accessibility to a wireless link. Also, we can further increase the efficiency by using the dynamic node allocation technique. The dynamic node allocation is the most efficient node allocation method. As mentioned earlier, it divides the network into 4 quadrants, and it tries to allocate the nodes locally. When a job is assigned to the nodes which are far away, that is, the nodes are non contiguous in nature, then there arises the need for long range links. And since there are only 3 wireless links, then their coverage is maximized by placing them along the diameters of the folded torus network with almost equal angular separation between each pair of diameters. For dynamic node allocation, 3 different methods are used in this paper, and the comparison of results of each method is shown in the following slides. Now coming to on-chip routing. Generally, we use dimension order routing, but in this case, XY routing is used. For routing in the presence of wireless shortcuts, we need 2 informations. One is about the wireless links closest to the source destination pair, and second is the bandwidth provided by such links. This information is known beforehand and is available to the router. And based on this knowledge, the router chooses a path via the wireless shortcut if that entails fewer hops to transfer a message between source destination pair. The message follows deadlock-free south-west routing when involving wireless shortcuts, and XY routing when following wired-only paths between a source and a destination. These are the experimental results depicted in this paper. Each diagram shows the comparison between various allocation techniques along with the wireless shortcut links. Each comparison is done for size of 64, that is multi-core size of 64 as well as for 256. This diagram shows the computational throughput comparison across different network architectures, system sizes, and job loads. And this shows the comparison between the energy consumption across network architectures and system sizes. This diagram shows the average power dissipation in different NOC architectures and system sizes. And this diagram shows the average and standard deviation and also the skew of fleets routed per network switch across NOC architectures and system sizes. So in order to conclude, we can say that the paper presents a high throughput and energy efficient hardware accelerators based on network on chip architecture, and the on chip network is built using both wired links and on chip wireless links. The wireless links act as long range shortcuts to further reduce the inter-core message latency. In addition to achieving high throughput, it is shown that the many core accelerator platforms are highly energy efficient. And we have obtained a computational throughput of over 10 power 11 operations per second. And here we have used logarithmic and exponential operations here. That is why it is mentioned as 10 power 11 log or exponential operations per second. We also found that each operation is consuming approximately zero point 0.5 nanojoule of energy. And it is also shown that the proposed architecture with uh, the system core size uh, 64 dissipates 55 watts of power and 213 watts of power for system core size of 256. And the maximum on-chip temperature is at 77 degrees Celsius. Also, the traffic behavior is analyzed through statistical properties. Several NOC architectures are explored and also evaluated them with respect to the above mentioned parameters and presented design trade-offs between throughput and energy efficiency and on-chip thermal variation. All the results presented herein provide solution to several challenges in a system architect faces when designing low energy and high performance many core hardware accelerators. So it is a very much promising systems since several challenges or drawbacks are here provided with the solutions. So that's all about the paper. Thank you so much.